All right, we want to talk about what's special about machine learning. We talked about the fact that you could have some sort of a relationship with things with some pattern out here, and you could do basically a linear relationship between these kind of things. And I showed you an example of linear with TensorFlow. It's not a very complicated example. It's just past hello world. We're going to be doing the lab this week. I want you to get through a lab that actually does some classification. I'm giving you the code. It's a matter of taking it. We've got two different ways of doing that, either on your computer, okay, or on Google's cloud computer, Colab. Okay, and I'm going to run through a video with each with doing this so that you've got a video, depending on what works in your environment, of doing one of these two things. So in both cases, what you want to do is you want to start out with a piece of code that basically does a hello world with TensorFlow. Make certain you've got it loaded so that you can actually work with it. And once it runs, okay, then we're going to talk about now what is special about actually doing some learning that makes some sense. I mean, there's value to this kind of learning. Okay, we can do statistics, we can do some analysis, and certainly, I've used this in production software for certain kinds of simple learning things, but it's not what I would really call machine learning that is useful. There's a recent study that came out in just a few days ago about a machine learning system that they're using for truck driving, and an analysis of truck driving that actually showed that somewhere around 50 to 90% of all long-haul truckers could be replaced with machine learning. It's a better learning system than this kind of a thing. So let's take a look at why we want to do machine learning that does more than just, give us a straight line that says some stuff are above or below the line. Let's say we have some data, okay? Let's say that we want to take text and we want to separate out spam emails from emails that are actually really used. And when we do this, what we'd like to do is be able to say that, we've got some spam in there, and the spam is these blue dots, okay? These are our unhappy ones that I'll just put in as X's. And it's distributed around something like this, okay? But we also have some data that says that we have real mail, and this real mail looks something like this. Okay, so we want to keep these guys and get rid of the others. Okay, now we could build a training set that like figures this out. Now we could use our linear thing and say, it doesn't really linear very well. Okay, but we could build a training set that says that this is where we're going to pick out what constitutes the good mails from the bad mails. So all of these are the good, and all of these are the spam. Okay? The problem with this kind of a learning approach is that although this will actually give us a set of values, it doesn't give us a very teachable set of things. It basically says, okay, now what happens when I put in some new values here, and I'll just mark these with the little ends, and these are, maybe this is spam, okay, maybe this isn't, okay? And we want to take these guys and say, are they good or are they bad? And now do we have to have a completely different training model that says, well, we want to include this one and we want to exclude this one, okay? And we went up with a really weird set of things, okay? So if we've got a model that exactly matches our data, okay, and it takes our data and says the exact input, okay, has those things in it, we can train it for that, but it isn't going to have any inference. And being able to infer for new stuff, whether it's good or bad, is what we're really after. And this inference for new data that we've never seen before is what's powerful about machine learning. It's not, can you drive down the exact same path that you already drove down once in the truck? The question is, can I drive down a completely new path, okay? With new cars and new things happening, and infer how to do it correctly on new data. And this new data is what we're really interested in. Now, it turns out that a long time ago we actually did a bunch of research on this kind of a subject, and we figured out how to do this for scientific stuff. And that approach for doing it applies to our machine learning. we can say we want to keep the model as simple as possible and have a high rate of accuracy. Okay? And we don't necessarily know what the features are in our data that are going to result in classification of the data. So if we have some particular piece of data, we've got an image, okay, and it's got a pattern out that looks like this. And we've got another one that has a pattern that looks like, okay, this, okay? So, I don't know what the features are that make this a shoe and this a t-shirt, okay? But I don't necessarily have to know what those features are. If I train my model that things that look like this are shoes and things that look like this are t-shirts, okay, then it can infer when it sees a completely new thing that it's never seen before that looks like this, okay, that is not what it saw before, okay, that must be like one of those. Okay, so we've got a way to take new data and say, this thing is similar to this other one. Okay, so that's the power of machine learning. It's this inference piece. And that's what we're after out of the machine learning. Now what we're going to do is I'm going to walk through a piece of code that basically does 9 different categories of different things. With shoes, ankle boots, t-shirts, dresses. And the images aren't very big. They're 28 by 28. And we're going to go through the process of cleaning up those images so that we can actually do machine learning on them. And then we're going to test whether or not it works. Now to do this, we've got to have a lot of data that already says what it is. That they're shoes, they're t-shirts, they're dresses. And it turns out that collectively, we have a training set of 60,000. So this setup here is 60,000 big. Okay? And 60,000 is enough to train something simple like this. But what we've done is we've got a separate set of 10,000 images to test it on, to see how good the inference is. And so we'll train on 60,000. We've got randomly picked 10,000 out of this set that we've also got classified that we can test our inference, and we can see how good a job do we do. And then we'll take a look at, not just how good did it do, but we'll actually say, if I picked one of these things and tested it, would I be able to predict, is it a shoe, is it a t-shirt? Okay, so let's go take a look at some actual code and walk through it. And this is the code we're going to use in this week's lab. So the code is checked in. It's not for you to come up with this code, but to give you an idea of how useful this code is, okay? This is basically the exact same thing. I mean, this is a network with 3 layers. So the inputs, you've got the image, you've got the inputs, and those connected to a hidden layer, okay? Okay, so these guys all connected to an output layer. So it's only a 3-layer thick network, just 3, okay? When I use this for actual real work, I actually went to a 5-layer thick network. So I added some more layers in between so that it could recognize more features than just this. But basically, this is enough to do classification with tagged data. Tagged data means that we already know those are shoes, we already know those are t-shirts. So let's go take a look at the code, walk through the code, run it, see how it works in both of our 2 cases with Colab and not, and work from there.